Hi, welcome NCAS Scholars. I'm Maria Chambers. I am the program coordinator. It's nice to meet all of you in person through the internet. So I'm excited you're here today. And now I'm going to introduce you to, oh, you can't hear me? Oh, okay. Can everyone hear me now? Yes? Some of you can. If you can't, then you probably need to check your system and turn up your volume on your computer. And underneath the picture is a volume control button. So now I'm going to introduce you. I'm not yelling. Thank you. I'm going to roll over and try not to leave a hole in the floor. Hi, everybody. This is Alicia Batteroni-Cortez. I am the NCAS Program Manager here at Johnson Space Center, and we are so excited to welcome all of you into our first live video chat with a NASA expert. We just want to set some ground rules before we get started. We see how excited you are from all of your comments in the chat window, and we were very impressed by the drawing that you had created on the whiteboard when we came in. And so it's all a testament to your enthusiasm and your excitement, and we love it. But to keep things running smoothly for this session tonight, we are going to, we already have disabled your microphone and your video camera, and during the talk we are also going to disable the chat window so that you can focus on the wonderful things that Dr. Vasavada is going to share with you. And then at the question and answer time, we will turn that chat window back on so that you can participate, and we'll ask you to raise your hand so that we can go in order and kind of manage the questions a little bit easier that way. So as you think of questions, you can start to type them in the chat window at the question and answer time, and when we call on you, you can hit enter and that'll pop up in the chat window. So you can sort of do a draft of your questions in the chat window and wait to hit enter until we call your name. So I'm going to go ahead and turn off that chat window right now, so say your last comments before we start, and I'm going to turn things back over to Maria so she can introduce our guest speaker for the evening. All right, and I'm back. Okay, so this evening we have a special speaker today. His name is Dr. Vasavada. He is the Deputy Project Scientist for the Mars Science Laboratory. Some of you have already got to Module 1, and you've already read about MSL and what it can do, and we are excited to have him speak to us today. This is a once-in-a-lifetime opportunity, so we welcome Dr. Vasavada.
Okay. Hi, everybody. I hope you can hear me and see me. Or at least, Maria, can you tell me that everything's working fine?
Yes, I can hear you loud and clear, and I can see you. Excellent.
All right. I'm just going to take it away. I'll talk for maybe 45 minutes or so, and then we'll take a bunch of questions. So as you heard, I'm Ashwin Vasavada. I'm here at the Jet Propulsion Laboratory in Pasadena, California, and this is where we run the Mars Science Laboratory with its Curiosity rover. As you probably have heard, we landed about 2 years ago, and we just had our 2-year anniversary on August 5th of this year. And so we're well into our mission on Mars, but we've still got a lot ahead of us. So I'll start just with some background of what the last couple of years has been like, and then give you a little preview of what we're doing in the future, and then we'll take some questions. But got a lot of information. I usually have way more than I can fit in 45 minutes, so I'll probably be going pretty fast, but that just means save your questions and we'll talk more later. Okay, so on the title slide, you can see this gorgeous view of where we were early, maybe about a year and a half ago. We were at this spot looking out across this big valley and towards this mountain in the distance, and you'll hear more about all this in the next few slides. So I think you're all studying Mars. Here's a little introduction about why we think Mars is so interesting. You can see here Earth and Mars. They're not close, this close to each other, of course, in the real solar system. But here you can see them side by side and get a feeling for how big Mars is. It turns out if you took all the continents around Earth and you squished them together in a ball, you would get the area that's on Mars. So Mars is a big place. It'd be like having to explore all the continents on Earth, including Antarctica, to be able to walk around all over Mars. Mars also, you can see, is orange colored. There's no water, there's no big ocean, but there are polar caps. They're right on the north pole of Mars. You can see in this picture, it's tilted a little bit towards the camera, and there's an ice cap. So there's actually quite a bit of water on Mars. We've known there's been frozen water on Mars. We've known that for decades and decades, but we continue to search for liquid water because it's a very dry place today. Although you can see a few clouds, there are some clouds over Mars, little wispy white things you can see in these pictures. On the next slide, here is some intriguing evidence that we got starting even in the 1970s, before all of you were born probably, but maybe not me. You can see these pictures that show a bunch of features that are all dry now, and these are big features maybe miles across. But all these things on these pictures, the best explanation for them is that a huge amount of water once flowed across the surface of Mars. In the upper left, there's some giant flood channels. These are channels carved by water flowing a lot bigger than like the Mississippi River flows today, that just scoured the surface and created these channels. In the lower part of the screen, there are some impact craters, like that ones that cover the moon. But in between these impact craters, there's actually little streams carved out, little river systems that have, and even ones that sort of braid and connect with each other, just like streams and rivers do on Earth. And then on the right side of the screen, this is a big landform that's all rock now. It's all bedrock now. But it once was a huge river delta. So like where the Mississippi empties into the Pacific Ocean, the Gulf of, sorry, not the Pacific, the Gulf of Mexico, and all that sediment comes out of the river and it forms this big fan of mud. You'd see something that looks very much like what this picture is if you were to dry up the Gulf of Mexico and look at the Mississippi River Delta mud that's all settling out there. But now this mud is frozen into rock and preserved for us on Mars. So the point of all these pictures is that even though Mars is a super dry desert today, at one point, probably 3 billion years ago, there was a lot of liquid water. And that makes it really interesting for life. One of the things that we are most interested about in understanding Mars is whether there may be life on Mars. And like this slide says, Mars resembles Earth in a lot of different ways, especially in its early history when we have all this evidence of water. And now you can see on this picture, Mars, this is like a little artist's conception of what Mars may have been like 3 billion years ago when it might have had a huge ocean in the northern hemisphere. And that ocean maybe had a water cycle like we do on Earth, like we have on Earth, where water evaporated, formed clouds, and then it rained somewhere else and caused those rivers to flow. And so this is what Mars may have been like. And so what we're trying to understand is whether there's any other life in the universe. That's one of NASA's main goals these days, is to figure out the potential for life outside of Earth. And for Mars especially, because it's our nearest neighbor planet, or at least the one that's most Earth-like and we can explore. It's easy to access. It's our neighbor, and it's something that it's a planet that 3 billion years ago looked a lot like Earth. So you might ask, are we looking for signs of life on Mars? We've done that. We haven't found anything easy, put it that way. We haven't found dinosaurs. We haven't found birds flying in the air. We haven't even found plants or anything like that. And we've even, in the 70s even with the Viking landers, we even did pretty sophisticated chemical experiments to look for traces of bacteria or other living organisms, and found nothing. And so it's actually, we've ruled out most of the easy kinds of life to find on Mars. And in fact, it's gotten to the point where it's actually difficult to send instruments to Mars to look for even fainter and fainter traces. But what we can do is ask a different question, and it's a question that a rover like Curiosity can answer, more confidently than the kind of experiments you have to send to Mars to look for this really faint evidence of past life. We can ask, was Mars ever a habitable planet? Now, the fact that it might have looked like this picture and how it's water, you might think, well, of course it was habitable. But that's not necessarily the case. What if this water wasn't fresh water? What if it was not the kind of water that organisms could use? Just because a planet has water, even liquid water, doesn't mean it's a habitable place. What if the water was fresh and usable, but there was too much ultraviolet radiation coming down from the sun because it doesn't have an ozone layer, it doesn't have a thick atmosphere, and all that ultraviolet light would just kill any chance of life developing. So habitability is beyond liquid water. It asks a whole bunch of different questions, which are on this slide. So here's a place on Earth that is actually a hard place for humans to hang out. This is in one of the deserts in California right after it rained. But it's a place that you would still call habitable. So, what do we look for when we're talking about habitable environments? We look for liquid water, life as we know it. You could dream up all kinds of science fiction life, but life as we know it on Earth all requires liquid water. So we think liquid water is one of the main things we're looking for on Mars to figure out if it's habitable. And then, like we just talked about, the right kind of liquid water. So you need to find the evidence of the water, and you need to carry some pretty sophisticated instruments to tell what that water was like 3 billion years ago. And then we want to look for the key chemical ingredients of life. There's the things that all of our cells are made out of, the carbon, the nitrogen, the oxygen, the sulfur, the phosphorus. These are all kind of the key building blocks of life that are in all of our cells. We need them to be on Mars if life ever had a chance. Even if there were even if we don't find them in living creatures, the fact that they're present on Mars means that life could have used them to form. And then finally, we need a source of energy. Life on Earth, a lot of life on Earth, plant life uses sunlight for energy, for its metabolism. A lot of other things like us, we gain energy by eating other living things, like plants and animals, and then you go all the way down the food chain until finally some tiny little animal is actually using some other source for energy, like sunlight or like a chemical energy. But we want to look for any kinds of energy sources on Mars that life could use. All right, that's a blank slide. I think what that slide was a picture of the rover showing all the instruments that we took to Mars. But I'll just summarize it by saying what made the Mars Science Laboratory so big is that, this is the 3rd generation rover from JPL here in Pasadena. The first one was kind of like this big, and it drove around, it had 6 wheels, and it carried a little camera on it, and it was really a test of whether we could design a robot to drive around on another planet. And that test was done in 1997, and it lived for about 80 days, but it was a success. And then in 2004, we sent 2 golf cart-sized rovers, and these had cameras, and then they both had an arm that could place an instrument up against a rock and kind of sniff the rock for the composition, the chemical composition, and take some close-up pictures with a microscope camera. And so they were, we like to think of these robots as robotic geologists, because really we have 100 geologists sitting here on Earth telling the robot what to do virtually for them. And so, the golf cart size one, Spirit and Opportunity, in 2004, had eyes like a geologist has eyes, has a hand, has a little microscope camera like a geologist would take out their magnifying glass and look up close at a rock. And it had a little ability to sniff the rock and see what it was made out of. But the real advance for the Mars Science Laboratory is in its name. It's a laboratory. So this is a huge car-sized rover that actually has 2 state-of-the-art chemistry laboratories built in the front end of the rover. So the entire front third of the rover body itself is made of these 2 very sophisticated chemical laboratories. And then we have a 7-foot robotic arm. It's huge. 7-foot robotic arm that places instruments up against rocks to sniff them like the other rovers did, but now goes one step further and actually has a drill, what we call a rotary percussion drill. It means the drill bit not only turns, but it pounds, it chisels while it turns. And it's the kind of thing like you might use to drill through concrete on Earth. So we have a really powerful jackhammer drill that gathers powder from the rocks and also can gather soil, and then it takes that soil and puts it into these laboratories on the rover and does these very sophisticated experiments to look for signs of habitability. Well, you can do all that. You can come up with a great science goal like understanding if Mars ever was habitable. You can build this great rover with these analytical laboratories, but it's all no good if you don't send it to the right place. And so we spent about 6 years looking at all the different pictures we have of Mars and all the other chemistry data that we can see from orbit. From orbit, we can tell what minerals are present on the ground, for example, and look at all those evidence of those dry riverbeds. And we wanted to find the one spot on Mars that we best thought might be a habitable environment that we could go study with this rover. And that's pretty difficult. I mean, imagine if you had to tell your friend who happens to be an alien from somewhere else, you had to go tell your alien friend, this is the one spot on Earth that you're going to figure out everything about Earth and everything about life and everything else. It's almost impossible, but we spent 6 years, like I said, finding what we think is the best place to send this one rover to spend its life, and answer these questions. And this place is called Gale Crater. It's shown here in this picture. Gale Crater is an impact crater, meaning 3.5 billion years ago, some giant asteroid hit Mars, created this 100-mile crater. And then what made this particular crater, out of the hundreds of craters that are all over Mars, special is the fact that it has this mountain in the middle of it. So when we looked closer at this mountain, we saw that that the mountain was actually made of layered rock. So this graphic shows if you were to cut the mountain in half and look at its inside, there's a whole bunch of layers of different rock inside. What was even more exciting to us is that this rock, it actually changes in composition as you go from bottom to top. So the fact that it's layered rock means that it didn't form with the crater. Sometimes craters have mountains in them just because the rock hit and then it bounced back a little bit and formed a little peak. But this is layered rock. This means that something brought in dirt over a long time and formed layers and layers and layers and built it up like a cake. And that means it left a record for us. So when you see layered rock, like if you go to the Grand Canyon, for example, one thing that's so cool about the Grand Canyon geologically is that the rocks on the bottom are, because they're on the bottom, because they're buried by everything on top, they're the oldest. The rocks on the bottom of the Grand Canyon could be like 1 billion years old, and then you go to the very top, and it might be some dust that fell out of the sky yesterday. So you have this whole sequence of time captured there, and that's what we hope to find in this mountain. You can also see that we landed, our landing site is that circle that's drawn on the ground next to the mountain. We couldn't land on the mountain itself, so we landed off to the side of the mountain, and that meant we would have to drive a long way to get to the mountain, which we'll talk about. But it also, we landed right on top of this ancient river system. So it's all dry now, but from orbit we could tell that there was a river that ran down from the crater rim and spread a fan out across the floor, and we chose to land as close as we could to that fan so we could study that even before going to the mountain. Okay, so we landed, yay, in August 2012. You probably all seen the video that, I won't go over that now, but it was like, awesome, and really glad it worked, because I had already spent about 8 years working on this project before we even landed. So, and me and a lot of other people, hundreds and hundreds of other people. So it was a huge relief for us to land successfully. And then when we woke up the next morning, we got this gorgeous picture back, which shows Mount Sharp, which is that mountain in the middle of the crater, right in front of us, although probably about 8 miles away or so. And when you're a robot on Mars, 8 miles is a long way. So we had our work cut out for us. But what you can see is we landed, in that picture in the upper right, we landed with this backpack that flew the rover down to Mars and then lowered it down on these ropes. And then we landed on our own wheels, and then that thing flew off and crashed, which was planned to do, leaving the rover behind. But in the process of landing, those rockets were firing. And those rockets actually scoured off the gravel from the surface. If you look in the bottom picture, off to the far right, you can see where the ground is scoured out and it's a little more gray. We looked in those gray patches with our cameras. Oh my gosh, I'm missing a whole bunch of slides. Can you see these? Or is everybody seeing a white screen, Maria?
Do you want me to try to reload the slides? Because I'm not sure why they're missing.
Okay. Yeah, it looks like they're not showing up for whatever reason.
Okay, do we want to take a couple of questions while I load the slides then? Just to...
Sure.
Okay.
Why don't we do that?
We'll enable the chat just while I put the slides back up. Okay, we're going to take our first question from Delora. And so, Delora, if you can go ahead and enter your question in the chat window right now. The question is, will we have a human exploration of Mars mission in my lifetime? And will we have terraforming capabilities?
Yeah, great question. I hope we have a human exploration to Mars in both of our lifetimes. You probably have better odds than I do, but we're working on it. One thing that was nice about Curiosity, in addition to all the stuff that I was talking about with delivering this big rover with labs and everything else, we now learned how to land something on Mars that was 5 times as heavy as anything we landed before. So we went from this little mini-sized rover to the golf cart-sized rover, and then to the car-sized rover, and we need to make just maybe like 1 or 2 more leaps like that in order to land humans. So even just designing Curiosity gets us 1 step closer. And there's a lot of different work at NASA going on now to figure out how to get humans to Mars. In between then and now, we're going to try to send something that returns rocks from Mars back to Earth, and that'll be like the next leap of learning how to bring things back from Mars. Because obviously, you know, there's a bunch of people who want to go to Mars on a one-way trip, but that's not what NASA's going to do. We don't really work that way. And so, you know, we need to learn how to bring things back from Mars too. We need to bring a whole rocket to Mars, and maybe even make fuel there, and then bring it back. So, I think we'll do it. And will they have terraforming capabilities? That, you know, probably not anytime soon. And then, of course, that's a really interesting discussion whether we even want, you know, whether we even should do something like terraform Mars. And I think there's a lot of things beyond science there and technology. There's even ethical questions about, you know, do we change Mars from what it is? But thanks for the question.
Okay, our next question we are going to take from the next person whose hand is raised. This is JKB. If you can go ahead and enter your question in the chat window. And the question is, have any fossils been spotted or located from possible life forms? Yeah, so far we haven't found anything that obvious that life has existed on Mars. So when we've been exploring Mars with these rover missions and landers before it, we haven't found any fossils. There has been some work on studying meteors that have come from Mars and then hit Earth. So this is pretty interesting. You know, like something big hit Mars a long time ago and created a bunch of rock fragments that got blasted off of Mars. And some of those fragments found their way to Earth. And we actually picked them up on Earth, and they turned out to be rocks from Mars. And when we looked at some of those, there was a group of people actually at Johnson Space Center, where the moderators are from, that proposed that some of the things they were seeing in these meteors were actually fossil evidence of life on Mars. That's still being debated pretty actively. We're not sure if that's, you know, really, it was really hard evidence to interpret, but so far that's the best we've got in terms of fossil life on Mars. Okay, our next question we're going to take from Ahmed. So Ahmed, if you would put your question in the chat window. Okay, looks like I see one from earlier. The question is there argon-38 and argon-36 in the ATM and the impact of that on terraforming?
So there is argon-38 and 36 and even argon-40 in the atmosphere of Mars. And these are different kinds of, for those who aren't aware what those are, so the gas argon in the atmosphere can come in different forms. And when you have molecules of a certain, or atoms of a certain kind of gas, they can exist in one of, like, kind of the form it's most common in, and then sometimes there can be these other versions of them that have more neutrons glued into their nuclei. And those, so there's one that has 36, and then there's one that has 38, and there's one that has 40. But they're all still argon. And what's interesting about those is that in kind of a, we think, Mars formed with versions of those gases that follow a certain recipe. Like there should be so many 38s for every 36, and there should be so many 40s for every 36. And it actually can take something big to change those ratios. And it turns out that Mars, the argon in Mars' atmosphere, is actually missing a lot of the heavier versions. There should be more 40s and 38s given the amount of 36s there are, but there's actually some missing. I'm sorry, I'm saying that backwards. We're actually missing some of the lighter ones, the 36s, and we have too many 38s and 40s. And what that's telling us is that something's caused the lighter versions of those argons to be lost over time. And what we think has happened is that it's telling us that Mars' atmosphere used to be thicker, and now it's thinner. And that's the same thing we can see when we look at two different versions of hydrogen, and we can also see it in different versions of other elements as well, including carbon dioxide. So it's pretty cool that we can look at the atmosphere, and even the different elements in the atmosphere itself retain the signature of the past. So by looking at the present atmosphere, we can figure out that something is off, and the fact that it's off in these ratios of the different isotopes tells us that a lot of the atmosphere was gone. And that explains, why it's so dry today and so wet in the past. It looks like we're still missing a bunch of those slides. So could try the PDF version if you still have that. Or I could just sort of try to work my way through the ones that are there. Maybe there's, okay, now it's better. So I'm going to go on. Okay, this is where we left off. When we last talked, we were landing, and we were blowing off the gravel from some of these spots. And then we looked with our camera at those spots, and this is what we saw. This is where all the gravel was removed from the surface, and what it left behind was this weird-looking bedrock. So normally, in all the times we've been on Mars before, when we've seen rocks, they've just been big, single rocks that are all kind of the same rock. This looks like asphalt, you might say, or like a sidewalk, concrete. It's that kind of thing. It's a rock that's actually a bunch of smaller rocks cemented together. We've never seen this kind of rock on Mars before. One of the ways this can happen on Earth is that something is transporting a whole bunch of pebbles, and maybe some sand, and then maybe water mixes into it, and it causes some chemistry changes, and then it all becomes stuck together. But this was only like the first week of the mission, so we didn't want to get too excited. But then we kept going on, and we saw more of it. And here's another piece of it that really does look like someone cut the sidewalk up in front of your house, and then these pebbles fell out of it. And when you see that little pile of pebbles on the ground on the left, those pebbles are actually kind of rounded. I mean, they're not perfectly round, but they're a lot more rounded than you would just get naturally, like if you just took a hammer and broke apart rock. When rock breaks up in a dry environment just by cracking and falling apart, it usually breaks up in big angular shards. The fact that these are rounded, and they're even rounded when they're still cemented in that conglomerate rock, in that rock made up of smaller rocks. The best interpretation here is that these actually are evidence that we were driving through the remnants of an ancient stream bed. That one that we landed on that I showed you from orbit. We landed on this fan of material that water had flowed down, spread in a fan, probably transported rocks and pebbles, and then water flowed through it, and then it cemented it all together. And so here we are actually driving through one of these ancient stream beds on Mars, and what caused the pebbles to be rounded is probably 10 to 15 miles of being tossed and turned in the stream bed, flowing to where we actually found these rocks. So that was our first evidence that we were finding something pretty amazing. So this is a cool picture. This is actually a picture from orbit taken by a satellite on Mars called the Mars Reconnaissance Orbiter. It's about 200 miles above the surface, has a huge telescope on it, and actually looks down and takes pictures of us every once in a while. So we landed at that place called Bradbury Landing. You can see the marks we left on the surface from our rockets. And then we drove, you can actually see the rover tracks. We drove from left to right across the picture. And you can even see Curiosity sitting there at the edge of this thing called Yellowknife Bay. And all that place in the upper right where the rock is a lighter color is that fan that we saw from orbit. That fan where water once flowed and spread material out. So we wanted to head over there. So we drove over there. We got closer, and it started looking very different. So instead of that gravelly surface that we landed on, all of a sudden we saw this very smooth bedrock, and we were pretty excited because this is what you might expect to find if you're seeing the sediments that float in water that are very fine, very like almost silty particles that when they dry out, they form mud, and that mud turns into what we call mudstone, and that mudstone is very smooth and bland like this rock here. When we got close to Yellowknife Bay, we started seeing this other kind of rock too. Now these are really platy rocks that have all been eroded and broken up now, but they used to just be very thin sheets of sand. And when we looked at the sand, we were like, well, this could be sand dunes, petrified sand dunes. But we looked up close, the sand grains were actually fairly big. They're too big to be blown around by air. And so these are actually, okay, let's see. Something happened with the slides. I think we lost whoever was sharing the slides. But what those platy rocks were telling us was that the water was actually carrying the sand and making it flow,
okay,
kind of like
Dr.
in the
Vasavada,
bottom of a stream bed, pushing the sand along the bottom.
Tell me which slide you want me to go to. I'll go to the number. So, because I just have your PDF. Okay. So which slide? Okay.
Yep. Let me check. Let's go to 15.
Okay. Oh, it takes.
Okay. So then when we got to this place called Yellowknife Bay, we deployed our arm and we started looking at it up close. And this is what it looks like when we deploy our arm and we started using the camera and chemistry experiment at the end of the arm to see what this was made out of. And on the next slide, this is when we actually drilled into that very fine-grained mudstone. What was immediately pretty cool here is that the rock, when we drilled into it, was no longer orange. This was gray powder inside. And you know what's so cool about that? Well, what's interesting about that is that the orange nature of Mars is a lot of it's because it's been sitting out on the surface for a long time, billions of years even. And chemistry in the atmosphere is sort of breaking down the pure minerals that once were in the rock into more broken down products through things like oxidation, like when iron rusts, for example. That also will destroy evidence of any past life or even any carbon-containing molecules like the kind we're looking for. And so the fact that the dirt inside the rock was still gray, still kind of pristine, was pretty cool. It made us pretty hopeful that we're going to find something important. The next one. Well, we drilled those holes. They're about the size of a dime, and then we delivered that material into our chemistry laboratories. Now, these are pretty sophisticated instruments. I won't be able to explain exactly how they all work, but one thing that you could see in the upper right-hand corner, things that look like rainbows. And so one of our two big laboratories shines X-rays through the rock powder that we dump into the instrument. And just like when you shine light through glass and it forms this, or through crystals, and it forms these rainbow patterns, all minerals are made out of crystals. And when you shine X-rays through them, every mineral forms its own unique rainbow pattern. And so we get these things called diffraction patterns. These are X-ray diffraction patterns by shining X-rays through rock. And we can read those rainbow patterns to figure out exactly what minerals are in the rock. And what we found is that the rock was made 20% out of clay minerals. The clay minerals are exactly what we were hoping to find. Clays only form when a lot of liquid water has been interacting with the rock for a long, long time. And so the fact that we found these clays in these rocks on Mars means that this probably was what we were hoping was we were at the end of this stream bed in an actual ancient lake, and we're sampling the mud at the bottom of that ancient lake that has all become, a lot of it's become clay. It also told us that the water had a moderate pH. pH, if you remember from chemistry class, that means it's acid or base. And so the fact that we had a moderate pH water, meaning it wasn't too acidic, wasn't too basic, that's the kind of water that's most favorable for life. And on the bottom one, you can see the results from our other lab, which is our mass spectrometer, showing all the different kinds of gases that came off as we heated up the powder of that rock to different temperatures, and different minerals broke down and released gases, and that's another way we study these rocks. And on the left then, you can see our big conclusion from this area at Yellowknife Bay is that everything we found at this site, this ancient lake bed, helped us conclude that Mars actually was capable of supporting life. We went to Mars to figure out if Mars was habitable. If we knew there was water, but did it have that those key ingredients of life, the carbon, the oxygen, the sulfur? You can see in the mass spectrometer results, all those things are there. We even found phosphorus and nitrogen as well. And then did it have energy for metabolism? Of course, we had sunlight, we have other sources of energy. We also had chemical energy for life. Some of the minerals that we found in these rocks would provide sources of energy for microbes, similar to how microbes live underground on Earth and use chemistry to power themselves. Next one, please. So I think I just went through all this, and so in the interest of time, we're just going to go to the next slide. This is all our evidence of life. Not evidence of life, evidence of habitability. We haven't found life yet. Still looking. Okay, this slide shows one other thing that we were able to do is actually determine the age of the surface. We've never done this before on another planet. So we used our mass spectrometer to look at different kinds of chemicals in the soil that are formed by cosmic rays. Now, cosmic rays are these rays of radiation that are always hitting Mars, and when these high energy rays hit molecules in the ground, they can actually cause atoms to break up and form other elements. And some of these elements that form, like helium-3 is a famous one, only really form by cosmic rays. No other natural thing on Mars would form them. So we searched with our detailed chemistry labs how much helium-3 there was, and we also searched for krypton, Superman's favorite element, And I think there's another one, neon, a version of neon that's only formed by cosmic rays. And by counting how much of those things were in the soil, we were able to figure out that this surface that we drilled was about 80 million years sitting on the surface. And before that, it was buried. And we think it was buried because the wind has been blowing for a billion years at the site and slowly eroding the rocks away. And so where we had drilled, there 80 million years ago, there was actually rocks on top of it that have now been eroded away by the wind. And why is this important? It's important because those same cosmic rays and other kinds of radiation and the ultraviolet light, like we talked about, all will damage evidence of past life on Mars. So the fact that we can find a relatively young place, like only 80 million years old, compared to the 3 billion years that the crater's been there, means we can use things like geology, this natural erosion, to find places to go look for life with future missions. Next one, please. Okay, so then we headed out. You can see where we landed in the upper right, and then you can see Yellowknife Bay marked there. That's where we made these discoveries. And then we headed towards the south and west, in other words, down and to the left. And we had planned some stops at a place called the Kimberley, and we had planned another stop at a place called Murray Buttes. And then eventually we want to get to that place that's circled because the entire bottom of the picture here is the foothills of this mountain that we want to get to. So next one, please. But we ran into trouble. So this is space exploration, and nothing's super easy. And the thing that, we knew we'd have some trouble on this mission. It's not going to go perfect when you're exploring Mars. And so the thing that ended up catching us unexpectedly was the damage to our wheels. Now we have pretty beefy wheels. In fact, they look like this. They're pretty huge. So you imagine how big the whole rover is if the wheels are this big. But the wheels are made out of aluminum, and they're pretty thin, and they have these treads in them that keep them strong. But in between the treads, there's just thin sheet metal. And we designed the wheels to make sure that they were strong enough, both to land on and then to drive around. But we didn't, I guess, fully appreciate how small, sharp rocks would dent the wheels, and then slowly those dents would become larger tears, and then those tears could lead to eventual failure of the wheel. And so we first discovered how much the wheels were dented around the 400th day of the mission. So we've been on Mars over a year already and driven a lot of miles. And we expected to see some wheel damage, but the amount of denting and even little punctures that we saw around this time frame were a little scary. Next one, please. And this is one of the things that had started changing right before that 400th day of the mission. We had gone from the smooth plains that you see in the upper picture to a terrain that had a lot more of these embedded rocks. So when you're driving over gravel, and even if there's isolated rocks and the whole rover pushes down on some of these rocks, they're on gravel, and so they just kind of sink in the surface and there's no damage to the wheels. But when you start driving on these rocks that are embedded, meaning that some of these rocks are like icebergs, they're like, there's a rock and then there's a huge, bigger part of the rock buried underneath, and so they're not going anywhere. When the rover wheel puts all its weight on it, it doesn't push in at all, and in fact it could damage the wheel. Next one, please. And so we started getting in situations like, this is sort of the classic picture. We got back one night and we're like, oh, that's what's happening. And so here's a rock that, in previous parts of the mission, we would have just broken it. It would have, buried or sheared off. But in this case, this rock wasn't going anywhere. And in fact, you can see it, the whole weight of the wheel and the rover on top of it is being rested on the top of this pointy rock. Next one, please. But it wasn't just that. We immediately went to our test models of the rover back here at JPL and tried to figure out, why, how could we have been so caught off guard by this? So we did things, simple tests, just like taking a pointy rock and putting the weight of the rover on it, accounting for the lower Mars gravity. And it turned out if you just rest the rover on a pointy rock, it doesn't break the wheel. It doesn't poke a hole. So something more was going on. And to make a long story short, it has to do with kind of the way our suspension system works. If you think about the fact that, like, some of these, the ones with the red arrows, the struts are pointing down. And it's kind of like taking your wheelie bag at the airport and pushing it instead of pulling it. And if you're pushing your wheelie bag and you hit a curb, your bag isn't going to just hop over that curb. You're not only going to push it into the curb, but because the handle of your bag is sort of pointing down, your forward pushing of the bag is actually going to result in a downward pushing of the bag against the curb. And that's what was going on. Once a wheel encountered a pointy rock and was struggling to get over that rock, the other wheels were still moving and pushing that wheel even further and harder into the rock and pushing down on the wheel into that rock. And that's actually what was causing these holes to appear. Next one, please. And so this is kind of a summary there. We had metal fatigue, like when you just bend a paperclip too many times and it eventually breaks. And then we had punctures from these rocks. So we had to figure out what to do about it. And so, one thing we thought about was, someone asked me once, like, do you guys have one of those things like at IKEA where you where the cabinet door opens a million times, or this robot sits on the couch 100 times? Well, yeah. Next slide, please. We did the same kind of thing. So we wanted to actually figure out how the wheels degrade over time. And so we built this rig at JPL, and this thing is basically half of the rover, and it drives in circles day and night. And we can place different kinds of pointy rocks in front of it, and you can see that middle wheel that's been going for probably 40 or 50 miles, much longer than the rover on Mars will ever need to go. That wheel has become pretty shredded. But now we've learned a lot by doing these tests. We've learned exactly how the wheels fall apart over time. Next slide. And so then the challenge was, how do we, now we know what's causing the damage. We know how to predict the future damage because we've done these tests. Now, how can we pick safer terrain to drive over? And so this is one of the things we did, a whole bunch of exercises to figure out how to find safer routes with less pointy rocks. Sounds simple, but it's Mars, and so it required a lot of work between the engineers and the scientists to find safer routes. I think let's jump over then to slide 33. So, started out with our big discoveries at Yellowknife Bay, this habitable environment. Then we got delayed for several months by this wheel damage. Now we're finally at this place called the Kimberley, and I just want to tell you a little bit more about our second scientific site here. You can see that there's multiple kinds of rock in this image. So this image is several miles across. We're looking down again, actually maybe about a mile across. We're looking down from orbit. You can see Curiosity there in the middle. And then you can also see there's different kinds of rock, including right above Curiosity, there's the rock that kind of goes in these, kind of has a linear pattern to it, going left to right in these lines. And we were interested in that because it might be more of the kinds of rocks that are laid down by flowing water. Next, please. Next one. There it is. So this is what that rock looked like, and in fact, it was more of that sandstone, those fine platy rocks that are made out of a bunch of sand with the sand grains too big to be blown by air, and so these are actually underwater sand dunes that move across as water drifts and carries the sand with it.
Dr. Vasavada, so we're at our 10-minute mark, and so we want to know if you wanted to keep going through the rest of your slides, or do you want to go ahead and skip to the Q&A? It's up to you.
I think I will wrap it up really quick, and let me just tell you what's coming. So to make a long story short, we drilled another hole at the Kimberley, and we're studying it right now. It looks like it has more clays in it. So a lot of the other area we're seeing still has all this evidence for water. And then let's finish up with slide 39. So this slide, which we can just leave up, is a picture of now we're closer to Mount Sharp, and over the next 2 years, this is where you'll see Curiosity going. We're finally about to cross over this big valley into the foothills of Mount Sharp, and it should be pretty cool. And it's already really gorgeous, and there's these 4 different rock types that all are in Mount Sharp, and all will tell us about the history of Mars. And so that's for the next 2 years.
Okay,
and
for the question policy, you will raise your hand, but do not hit enter until I call your name. So you can type your question in the box, but do not hit enter until I call your name. Wow, that's a lot of dings. All right. We're going to go with Lily. Lily, you have your hand raised. You may go ahead and hit enter. Sorry, we will undisable the chat. Okay, Lily's question is, how come we restrict our search to liquid water, not liquid other substances? I know water is life as we know it, but doesn't that mean we're limited in our exploration?
Yeah, great question. I mean, you have to start somewhere, and water is a pretty amazing chemical. You know, so it's not just that it's life as we know it on Earth. Even when you start thinking about what other life forms might use for a liquid, water just has very unique chemical properties. That anywhere in the universe, water is still water and will still have those unique chemical properties. So, you know, we think life is pretty likely to use water even in other forms and other places. And also, you know, you just have to answer what you think you have the best chance of understanding. And since we have so much experience with life on Earth using water, you know, we search for it. But of course, we do have the ability to look for other chemicals as well, and we every day we look for other things.
Right.
But in terms of habitability, we focus on water.
You may hit enter for your question.
Next one, please.
Do you think that there might be the potential for life or any valid discoveries on Mars' moon?
Yeah, you know, you never know. One thing that's really interesting about Mars itself, the planet, is that it does have all this evidence for ancient water and a whole hydrologic cycle, you know, like something carved those channels, then probably rained out and made streams and all these other things. And life would, you know, probably require a stable, habitable environment like that. It's a little hard to think how something like Mars' moons, which are very small, too small to ever retain an atmosphere, and exposed to all the harshness of space and cosmic rays and all those things, you know, you could always think of some exotic life form that might be able to survive there. But when you're looking for a place that was so friendly to life, that life even had a chance to evolve there, like it did on Earth.
Chance Mitchell, go
the
ahead.
Planet's probably much better.
I'm sure a lot of thought has been put
into
into where a human mission may land or set up an establishment. Is there a front-runner location, and what advantages does it offer?
Interesting question. I don't think we've gotten too far down that road with where humans might go. I can think of 2 things that might start the conversation. You know, one is that we like the equator generally because, like on Earth, it has the most benign weather. You know, it's kind of warm most of the year. But on Mars today, the equator is also pretty dry. So another place humans might want to go is like the North Pole, where there's 3 miles thick ice deposits, you know, and you might be able to use that water to support the human mission. The problem there is that, like on Earth, for half the year, the polar regions on Mars are really cold and dark. So if you just had a short human mission, you might want to go to the summer in the North Pole, and you have all this ice water available for you.
How many satellites are required to properly support Curiosity? Are there ever times that we lose signal due to line of sight issues?
Yeah, in fact, Mars spins on its axis once every 24.5 hours, just like Earth. So for about half the day, Mars is facing away from us, and we have no line of sight communication with it. But we do have these orbiters around Mars, and so we communicate both directly to Curiosity using big antennas on Earth, and we also communicate to the orbiters, and they relay our communication to Curiosity. And often we can do that, when Curiosity is not visible from Earth. So we talk to the rover actually once every day in the morning on Mars when Earth is rising with respect to the rover, and then we talk to Mars twice through the orbiters, once at about 2 p.m. on Mars and once at about 2 a.m. on Mars. Next one, please.
Did you hit enter? Oh, okay. Have you ever tried intentionally starting fires or causing explosions or planting water on Mars to get a visual confirmation of what happens? Any intentional contamination, pollution of the atmosphere to observe reactions, etc.?
We have a pretty good idea of what Mars' atmosphere is made out of. We've measured it very precisely, so we know how dense it is, and we know that it's almost all carbon dioxide. So we can do a good job of just simulating that on Earth. It's not a huge, we don't have like huge questions about how water would behave or how a fire would behave, because we can simulate Mars conditions very well on Earth. Having said that, we do have an instrument on Curiosity that fires a laser and creates little sparks. And we actually study the color of those sparks to figure out what the rocks and soils are made out of. And so we are every day firing a laser on Mars, creating little mini explosions. They're extremely tiny, and just like what we predicted based on laboratory experiments on Earth, when you fire the laser on Earth, it creates a little spark. When you fire the laser on Mars, the spark is actually much bigger, and that's because Mars' atmosphere is thinner,
Chris,
and the explosions are a little bigger.
What do you think about the possibility of privatization of space exploration, including future Mars projects?
I'm a big fan. I think it's great that that a lot of private companies are helping the U.S. at least, if not other countries soon, in the exploration of space. NASA, I think, will always be doing the really cutting-edge things because it takes the kind of government support, the many billions of dollars that our country puts into this to be able to do those very cutting-edge things. But now we're seeing a lot of private companies help out by carrying cargo to the space station, and some private companies are even trying to do more than that, like trying to think of human missions to Mars. I think it's great. I think as long as we're all kind of working together and sharing with each other, and kind of following good rules about treating Mars well, is also. We don't want to contaminate Mars. We don't want to crash things on Mars. So as long as we can kind of keep control of everything, I think it's all good.
So we are at 6 o'clock, the end of our chat, and we want to respect your time, so we understand if you need to go. But if you can have time for a few more, that'd be great. All right, so we'll go ahead and go to our next one. Omar, you're up. If you could redesign the MSL rover, what would you add or change to it? What new or emerging technologies do you think would greatly increase the capabilities of future rovers?
Boy, I'm so wrapped up in this rover, I hardly ever get to think about that kind of stuff. I live and breathe curiosity. So, I mean, obviously, if I could redo Curiosity as it is, I probably would make the wheels a little more thick. Let's see. I think, for the next rover, we're already thinking of more advanced experiments that actually could detect signs of past life. You might wonder why we didn't do that on Curiosity. Part of it is it's really cutting edge stuff. So as scientific experiments are being able to be shrunk down more and more and even put on individual computer chips, we take advantage of that. So even the technology that we designed Curiosity with maybe 6-7 years ago now, we already have next generation versions of all that we can use on future missions. But I love how Curiosity is even so much better than the ones before it. We just have fantastic HD cameras. We have very sophisticated labs. It's just going to get better with next missions as well.
Okay, Eric, you're next. Is helium-3 abundant enough to use as a viable energy source for future manned missions to Mars?
Yeah, I don't know the answer. I mean, we've talked about that. NASA's talked about that, on asteroids and on the moon, where those planets don't have an atmosphere and asteroids don't have atmospheres. So there's a lot more generation of helium-3 by cosmic rays than there might be on Mars. But there's still a good amount. So my guess is that it could be used as an energy source, but you'd also have to have a pretty big factory to probably sort through tons and tons and tons of dirt to take out the small amount of helium-3 that would be in there.
Did the streams form first or the craters on Mars?
We think the craters formed first. So the first maybe 500 million years of Mars history, from 4.5 billion years ago when the whole solar system formed, till about 4 billion years ago, is mostly there was probably a very different atmosphere. There was probably still bits of the early days of the solar system flying around and causing all these big impact craters. A lot of the biggest impact craters are from that early time period when the solar system was still sort of cleaning itself out from its initial formation. But then, the earliest times when there was a lot of liquid water are still very early. They still date from around the end of that time period. So it's possible that some, in fact, we know of some that are contemporaneous. So like there are some streams on Mars that an ancient stream, you can see it across the surface, and then there's an impact crater that went right on top of it and broke up the stream. And so, I think they overlapped for a little bit, but for the most part, the craters came
more
first.
questions do you want to take? Because we have a lot.
Oh, I'll go till.
Okay, okay,
I'll
so
go
next
for
we have
another
Sarah. Go
maybe
ahead,
like
Sarah.
4:15. Then I gotta go.
What does it mean to be deputy project scientist for your team? What is a typical day like for you?
Yeah, thanks for the question. So deputy project scientist means I'm a scientist here at JPL, where the rover was designed and built and tested and then operated. For the most part, the rest of the scientists on the mission are outside. They're somewhere else. They're at universities, they're at other institutions, and they participate kind of virtually, But at a place like Johnson Space Center or at JPL, where I'm at, there will be a number of scientists who are on that facility who are there really to interact with the engineers day by day as the rover or other mission is being designed and built and tested. So a lot of my job during the last 10 years, or at least the 8 years before we launched Curiosity, was to tell the engineers things about Mars. So I would tell them, well, this is how hard we think the rocks are. This is how deep you have to drill to get the stuff that we want. You know, this is the weather you can expect on Mars. These are the goals that we're trying to accomplish with the rover. So the engineers knew exactly how to design it. And then my job now is to deal with helping lead probably about 400 scientists around the world who participate in this mission. So as a project scientist, that's sort of it. You know, I'm a scientist along with all the engineers at
impressive.
JPL, and then I'm also helping lead the whole science.
Thank you. So next we have Jason. Let's see. Jason, did you hit enter? Okay, all right, he's retyping it. Would NASA consider Carl Zeiss again for their next generation of Acura systems?
I'm not exactly sure what all that is. I know Carl Zeiss makes good optics. We don't have any Zeiss lenses or anything on our rover that I'm aware of.
All right, Trenton, you're next.
But we do have 17 cameras. That's about all I can tell you.
Thank you for taking the time to talk with us, Dr. Vasavada. Do you think there's a possibility of an aerial robotic explorer to help explore larger areas of the Mars surface?
Yeah, I think there is. You know, there's been a few different attempts to build Mars airplanes and Mars helicopters, but so far none of them have gotten to the stage yet where we think we can actually fly it to Mars. So I think it would help fill in the gap. You know, we have all this great data we take from orbit, and then we can explore this little area just a few miles across, you know, with a rover. But what an airplane would do, as you described, is be able to survey, you know, maybe like 100, 200-mile area, and that would help us explore a lot more of Mars.
So next we'll do John, because you already hit enter, and then Jason. Dr. Vasavada, what types of possible fuel could we use from Mars to have a relaunch back to Earth? Where would you find it on Mars? And shouldn't the national contract of how to treat Mars be put in place soon?
National contract of how to treat. Okay, got it. Yeah, so Mars atmosphere is mostly carbon dioxide, and one of the two things that's in rocket fuel is oxygen. And so one of the ways you'd make fuel on Mars is to break down the carbon dioxide, CO2, into C and O2, and then use the oxygen for part of the rocket fuel. There's other things that I think people are working on as well, but so far that's the one that that's pretty promising, and we're actually going to try to make oxygen on Mars in the next rover mission to Mars that launches in 2020. In terms of the national treaty to protect Mars, there actually is one. There is an international treaty that's maintained by all the different space agencies around the world who explore Mars. So that includes all of Europe, and then Russia, and the US and Japan have all sent probes to Mars, and India is sending a probe to Mars that'll arrive next month. And so all these nations have agreed on a treaty that helps prevent contaminating Mars with Earth organisms until we're satisfied that we've done everything we can to figure out if life exists on Mars. And we're not at that point yet. We're still searching for faint signs of life. So every spacecraft that goes to Mars, if it's a lander, it's scrubbed and cleaned with alcohol, sometimes put in an oven and baked to kill everything so that we protect Mars. And then the things that fly to Mars in orbit, they can be a little dirtier, but they have to take extra steps to make sure they're not going to crash into Mars by accident. So we do have a lot of treaties in place already, and by the time we actually send humans to Mars, it's sort of over at that point. The moment the first human steps out of a spacecraft onto Mars, we contaminate the place because we're just full of microbes, and it's almost impossible to keep it clean. So we need to get this robotic exploration for life done before we get humans there.
Okay, has there been any sign of any plant life to have ever existed on the planet, and has there ever been large concentrations of water discovered, or only small concentrations in dried riverbeds?
Yeah, there's no signs of any life on Mars currently. So no plants, no animals, birds, no even bacteria or tiny little microorganisms. So nothing, you know. So I mean, it seems the longer we look, the odds kind of decrease, and life gets more and more hard to find. But we're still looking, and we still think, you know, maybe there's a chance we'll find something in the ancient past, you know, in these in the ancient rock record. And in terms of the amount of water, there's actually a huge amount of water, even just in these ancient streams and rivers. So to carve the big river systems that we see would have meant just a lot of water, kind of like a river on Earth that's just, you know, carrying a giant amount of water flowing continuously day and night, year after year for hundreds or thousands of years. And then today, on the polar caps, there's a giant amount of frozen water. If you were to take the polar caps on Mars and melt them down, they would cover Mars 30 feet deep in water. I mean, think about that. That's huge. You know, 30 feet deep, the whole planet would be covered in water, and all that water is now frozen at the poles. So at one point, maybe some of that water was in an ocean, maybe some of it was flowing in these rivers, but currently it's all locked up as ice.
Jose, you're the last one.
Sure, one more.
It's a long one. For this scholars program, we are required to design a rover to be sent to Mars. Do you have any advice or tips on how we should approach the project? Don't give them any hints, though. I'm sure you probably want the answers for this project.
I'll just mention some basic things which you're probably already studying. You got to keep in mind the terrain, like you point out with the wheels. Got to keep in mind the environment. You know, not only the hot and cold, but the thin air, the hazardous radiation that comes in, the ultraviolet light, for example. And then you just have to design it to very efficiently do the kind of science that your mission is there to do, or maybe it's a mission designed to carry humans. One thing that engineers always say is that you want to design it to be just to be able to do exactly the thing you need to do, and no more, no less. No less, you know, because you'll run into problems like the wheels not being good enough, and no more because it's really expensive and dangerous to get to Mars. And so every unnecessary thing that you put on your spacecraft means you need a bigger capsule to fly it in, which means you need a bigger rocket, which means it probably can't land as high up because you need more of the Mars atmosphere to swim successfully. And so all these different things, you know, you just have to streamline and really focus in on exactly what it's there to do, and then build it to do exactly that.
All right. Well, I just want to thank you for taking the time today to speak about Curiosity. I'm really impressed with everything that you talked about today, and I know all the students really appreciate hearing you speak. So thank you, and we hope you have a great evening, and I can't wait to see all of their projects to see what they can come up with.
All right. Thanks, everybody, for tuning in, and I've enjoyed it. Bye-bye.
All right, you're all free to leave the session, and remember your quiz, your first quiz for Module 1 is due by midnight tomorrow, so make sure you get started on it if you haven't yet. Good luck.
Woo-hoo.